Lesson 22, Blackbody Radiation. Part 1, the Blackbody Radiation Problem. In the late 1800s, scientists thought that they knew it all. They believed that light was a wave, and they had lots of evidence for that. Light reflects like a wave. It refracts like a wave. It diffracts and shows signs of interference when it travels through two slits, just like a wave. There was a problem with this, however. Scientists were not able to apply the wave model of light to explain hot, glowing objects. And even though this was a very small, trivial problem, we called this the blackbody radiation problem, it led to what scientists call the ultraviolet catastrophe, which led to a new physics called the quantum model of light. A huge amount of modern physics is based on this quantum model of light. We call this quantum physics. Quantum physics predicts that light is a particle. It's commonly understood that all hot objects give off light. For example, fire is hot and it gives off an orangey reddish color. Scientists found that hot glowing objects emit a continuous spectrum, with wavelength intensity peaking at a particular wavelength depending on the temperature. Continuous spectrum is a particular kind of light. If you pass the light of a continuous spectrum through a prism, you will get a continuous spread of colors with no gaps. All hot glowing solids or liquids emit a continuous spectrum. For example, a human is 37 degrees Celsius. While this is not terribly hot, humans still emit electromagnetic radiation because of their temperature. Humans glow with a continuous spectrum in the infrared range. The peak frequency of a human's temperature is at about 9,700 nanometers. Another example is glowing hot iron, which is around 730 degrees Celsius. Hot glowing iron glows with a continuous spectrum extending into the visible range, which is why glowing hot iron looks a little bit orangey red. The sun has a surface temperature of around 4,700 degrees Celsius. It glows with a continuous spectrum extending into the visible range, and the peak frequency of the sun's visible spectrum is green. Here is the visible light spectrum, bounded by ultraviolet light and infrared light. The hotter an object is, the more on the blue-violet end of the spectrum it will glow. If it's a cooler, hot glowing object, it will glow more reddy orange. Violet light is emitted by an object that is 15,000 degrees Kelvin or 14,726 degrees Celsius. A peak of bluey green will be emitted by an 8,000 Kelvin object or 7,776 degrees Celsius. Yellow light will be the peak frequency of a 4,000 degree Kelvin object, or 3,726 degrees Celsius. And it will be red if you have a 1,000 Kelvin object, or 726 degrees Celsius. A blackbody is an ideal radiator. It absorbs all electromagnetic radiation that falls on it, which means it doesn't reflect any back, and as a result it becomes hot and radiates light. Scientists studied hot glowing objects and measured wavelengths and the intensity of the wavelengths emitted. The results for temperatures ranging from 3,500 Kelvin to 5,500 Kelvin are summarized in the graph. Let's look at the 5,500 Kelvin line. It is a continuous spectrum, which means that wavelengths are emitted in the low region as well as in the higher wavelength region. But peak wavelength intensity for 5,500 Kelvin happens around about 500 nanometers, which is in the visible range. The blackbody radiation problem. Classical physics, which predicted light as a wave, could not explain the blackbody radiation curve. A scientist came up with a formula using classical physics, or light as a wave, to try to predict this curve. Don't worry, you won't have to know this formula or use this formula for any calculations. When you apply this law, you get the purple dotted line shown in this graph, which, as you can see, doesn't match the curve that's actually found in experiments well at all. Classical physics predicted the infrared region quite well. The two curves line up. But in the ultraviolet region, the intensity of the light was predicted to increase to infinity. It kept on increasing at a steeper and steeper curve. This is a ridiculous result, and it was referred to as the ultraviolet catastrophe because scientists were not able to use their current understanding of light to explain this problem. If the study of light represented your life's work, you would call this a catastrophe too. Part 2. Planck's solution to the blackbody radiation problem. Max Planck was a German scientist who offered a solution to the blackbody radiation problem at the beginning of the 20th century by suggesting that light is quantized. Quantization means that you can treat something like it comes in single quantities. For example, light would come in particles. We call these particles photons. The formula that Max Planck came up for a photon was E equals hf, where E is the energy of a photon, F is the frequency of that photon, and h is a number that we call Planck's constant. More on this later. Planck's formula, E equals hf, predicted that the energy of a photon increases as the frequency of that photon increases. And the energy of a photon is directly related to its frequency. Planck's quantization of light allowed him to develop a formula that very accurately predicted the blackbody radiation curve. Don't worry about trying to do calculations with this formula. It's just enough to know that when this formula is used, the curve of intensity versus wavelength is accurately predicted for any hot glowing object. Planck's constant has two versions depending on the unit of energy you are using. Both of these are on the formula sheet for Physics 30. If you're working in joules, use the top Planck's constant listed on your formula sheet. This is Planck's constant equals 6.63 times 10 to the negative 34 joules seconds. But if you're working in electron volts, you use the other version of Planck's constant. Let's stop for a minute and review electron volts. An electron volt is the number of joules an electron gains in 1 volt of potential. According to your formula sheet, an electron volt is equal to 1.6 times 10 to the negative 19 joules. So if you're working in electron volts, use the second version of Planck's constant listed on the formula sheet. This is Planck's constant equals 4.14 times 10 to the negative 15 electron volts seconds. For example, how much energy does a 700 nanometer photon have? We'll start by converting the wavelength of 700 nanometers into hertz, or frequency. This is 700 times 10 to the negative 9 meters. Since c equals f lambda, then f equals c over lambda, equals 3 times 10 to the 8 divided by 700 times 10 to the negative 9. This gives us a frequency equal to 4.286 times 10 to the 14 hertz. Next, we calculate the energy of the photon. According to Planck, energy is equal to Planck's constant times the frequency. Let's calculate in both joules and electron volts. In joules, we use the first Planck's constant. This is 6.63 times 10 to the negative 34 joules seconds times the frequency, which is 4.286 times 10 to the 14 hertz. This gives us an energy for our photon equal to 2.84 times 10 to the negative 19 joules. Occasionally, it's nice to work in electron volts because it makes the scientific notation much nicer to look at. So we can use the second version of Planck's constant to find the energy in electron volts. This is 4.14 times 10 to the negative 15 electron volts seconds times our frequency of 4.286 times 10 to the 14 hertz. This gives us an energy in electron volts equal to 1.77 electron volts. Second example. A 100-watt laser emits light at a frequency of 5 times 10 to the 14 Hertz. If it operates for 25 seconds, how many photons are emitted? The first thing we need to do is turn the power of 100 watts into an energy value. Since power is equal to energy over time, it's the rate of use of energy, then energy is equal to power times time. This is 100 watts times 25 seconds, which gives us an energy of 2,500 joules. We also want to determine the energy of a single photon. Energy is equal to hf. We want this in joules this time because the energy we have for the light bulb is measured in joules. So we use the first version of Planck's constant. This is 6.63 times 10 to the negative 34 joules seconds times the frequency of 5 times 10 to the 14 Hertz, which gives us an energy for a single photon equal to 3.315 times 10 to the negative 19 joules. So we have a total energy of 2,500 joules, and a single photon has an energy of 3.315 times 10 to the minus 19 joules. We want to find out how many photons fit into the total energy. So the number of photons will be the total energy divided by the energy of one photon. This is 2,500 joules divided by 3.315 times 10 to the negative 19 joules, which gives us a number of photons equal to 7.54 times 10 to the 21.